You're live, I think.
Is it?
No, you're live.
Yeah, fine. So, hello everyone. Sorry for the delay. I had some net issues. Uh, hope I'm audible. So, yeah, let's start with the session. So, hello everyone. I'm Vishwajit, and today I'm going to be taking your session unboxing LLMs, which is going to be from basics. So, you don't need any knowledge of LLMs, and I'll make sure you learn a lot of stuff today. So, without further ado, let's start with the session and let's have some fun. So let's move on to the session roadmap. So today we'll be covering at first what is an LLM. So basically, I think it's pretty self-explanatory, and we'll be moving on to types of LLMs. So there are two types of LLMs, and I'll be explaining what are they, and we'll be moving on to how do LLMs work. So how do these like really good AI stuff like work, and then we'll be moving on to how are LLMs trained. With that, we'll be moving on to APIs and prompting basics, where you'll be coding to get outputs from an LLM. And then we'll be moving on to prompting techniques. So there are various prompting techniques to which how you can code and ask prompts to an LLM. And with that, we'll move on to QLoRA. So the QLoRA is the most important part of the session because it involves fine-tuning LLMs, which is like the current most demanded thing in the market. So, and then we'll move on to a live demo project where I'll be showcasing a project which I built for a hackathon using LLMs, and the last question answer and the thank you session. So let's get right into it. So what are LLMs? So when you think of LLMs, you think something that, so what are LLMs? So if you think of LLMs, you think of tools like ChatGPT, Claude, like these magic assistants. You just put something and then they give a lot of results. Like, hey, give me this code. Give me a code to code how to center a div tag in React. So I think everyone should have coded it. And so they magically like give you the answers. So it's like a magic assistant. So you just give them a prompt and then they give you the result. So so how do these so this is just a high level overview of LLMs. So what exactly are LLMs? So LLMs are basically deep learning models. So they are basically AI models which are trained on huge data sets. So this started when Google released its new paper, which is called "Attention is All You Need," which introduced a new layer called transformers, which changed the whole AI world from 2017. And then we see the rise of ChatGPT and all that, and now we are here. Moving on to the types of LLMs. So there are two types of LLMs. So one is frontier models. So frontier models are something that are built by big companies, like let's say OpenAI, which is basically ChatGPT. If you say Claude, Gemini, and all that, which you use for day-to-day tasks. And uh, the the plus point of these models are they are like trained on really huge data sets, and they are really huge models. So they are quite accurate. So you can use them for a lot of things, and they are pretty good, but they are closed source. That is the only disadvantage of them, because you have to pay. It's pay per token. You can use ChatGPT for free, but then if you want something to use for your application, for your web application, you have to pay per call for API call. So I'll show you a basic like OpenAI website. Um, it's a pretty well documented website. So here you can see their API platform. Um, uh, can see the flagship models, and as you can see, input $15, output $60 per 1 million tokens. I will be explaining what these tokens are. So tokens are something I'll be covering. Different models have different price ranges. This is like a really powerful model, and then this is like a cost efficient model. And this is like a very good documentation because they're doing it for, like, you have to pay per token and all that. So moving on to open source, which we are more interested in, because we can't be using these frontier models on a day-to-day basis. We don't have like infinite money, right? So we'll move on to open source models. So open source models are something that you can download, run, and even fine tune. So basically you can fine tune these models to your own custom needs. So, and they're fully transparent, which means that you can see their architecture, you can see their weights and all that, and it's really good for building custom projects because it is open source. So there's a beautiful website which hosts these models. So I would like to give some time to it. It's called Hugging Face. So let's move on to Hugging Face. Yeah. So as you can see, this is Hugging Face. You can see a lot of things over here. At first it's like, oh, what is this? First you might have to sign up. I have already signed up. So you can see if you have seen about open source model, you would have definitely come across MetaLlama. It is one of the most famous models. So also while looking at this, keep a note of these numbers. There are like numbers like 17 billion. It looks like B 14B, the 17B. So there are these numbers. Keep a note of them. I'll be explaining what is that. So there are a lot of models like Llama, DeepSeek, which just changed the world recently. Uh, NVIDIA's Llama, Gwen, like a lot of models, like good models. And here you can find models, and inside models, one second, attendance. Give me a second, please. Attendance. Sorry for that. Yeah. So as I was saying, it is like a really good website. You can host a lot of models over here that you can use, which are open source, and there are also a lot of other things like you can see data sets. So there are a lot of open source data set. It's like GitHub but for machine learning. You can get a lot of training data over here for training your LLMs and even some other neural network models. And this is Spaces. So Spaces is basically where people host their own LLMs which they built, and then you can play around with it. I won't be doing much into it. And documents, enterprise, pricing. So one of the most important things is there's a Python library for this. So if I go into a model like MetaLlama, if I want to use this model, it's just a simple API call to use these models. There's a Python library called transformers given by them. So it's just like, that's it. This is the code to load the model and get this thing. So I'll show it to you on my Google Colab. So before that, to use these models, I forgot to tell, you have to generate tokens. So you can generate your API tokens over here. You can go to access tokens and you can create new tokens. I can't show it to you right now because my token will be visible. So this is not a thing I want. So you should go to access tokens, and in access tokens you can generate a token, and you can use this Hugging Face library, this transformers library, and use these models. For some models you might need some models are gate kept models, so you might need access. You have to like say for this model you have to give your first name, last name and all that, and then institution, because sometimes they need to know who's using the model. So for that you need to get approval. Once your account is approved, you can use some of these models, like MetaLlama needs that. Some of the models like Mistral don't need, but just like you can just do this and all that. I've already finished doing it. So now we'll move on to the coding area. So at first you can store your secrets over here in Google Colab. They have provided like a really good space for it. You can store like all the API tokens and all that. And you can and then you can use this code to extract these tokens. So this code is basically for logging in into Hugging Face. So from Hugging Face Hub, import login, and you're basically importing a token and storing it in a variable. And then now we are logging into Hugging Face. So I'll run this. Now I'll just show you a simple, like how simple it is to call a model. It's just like a chat GPT, but you can use it in your own code. Like you can use it for websites and all that. And I'll show you just how simple it is. You don't have to worry much about this. I'll be explaining it in detail later. And you just look at this prompt, and I'm going to prompt it. So let's run. It's taking some time. Okay, it's pretty slow. I think my net is like slow. I'm basically using CPU right now, so I think it's a bit slow because of that, because it's using CPU to generate the result right now. But should be right now, yeah, 42 seconds, and it just gave a result. And yeah, it's pretty simple. You can just give a prompt and then it gives you a result. And moving on, as just basing an AP call, I will explain the code over here later. So moving on. So how do LLMs work? You can ask ChatGPT a question, and then it looks like it understands what you're trying to say. But how is it even possible? How does it like understand what we are trying to say? But like how does it do is, so basically it converts. It doesn't understand the language exactly. It basically understands patterns. So it converts all our text into numbers, and these numbers are called tokens. So tokens is a really important word, but you would have remembered it when I told about OpenAI, or when I showed you the OpenAI document. So when you go over here, API platform, uh, view API pricing, yeah, you can see the exact word over here, 1 million tokens, which means 1 million possible words you can use. So this is what tokens mean. So I will show you an example. I will just go to my Google Docs. So let's just say you're giving a prompt like what is hello, how are you? So the model doesn't understand this. The model only understands numbers. It's basically mathematics in the end. So what it does is it splits. So basically it has like a dictionary. It has its own dictionary. So it's not. It's like it'll split it. It split this into hello, ho, w, r, something like a gibberish. Like some words you might understand, but it'll split into something like this. Different models have different splitting. Here this is just for an example, and this will be encoded into a number. So for example, hello will be given a number as like 20, let's say 20. HO will be given a number like let's say 30. Where will be given a number like let's say 40. U will be given a number like let's say 50. This is hypothetical, and then a question mark like something like 3213. So this is how the model like transfers your English language into numbers to basically pass it as an input through its layers. So I'll show yeah. So you can see prompt I have given what is photosynthesis. So let's run it. Yeah. So as you can see, the prompt is what is photosynthesis. So this model right here, which I'm using a small model, Facebook opt 1.3 billion. It's not that powerful because I wanted to be make it fast, or else it's like really slow. So you can see the tokens over here. So there is something called /s here. This is nothing but it is saying it's the start of a sentence. So basically a model needs to know when a sentence is starting, because that's pretty important, right? And you can see it's splitting what. And then this G is nothing but your space is. You can see this, it doesn't fully understand photosynthesis. It splits photosynthesis into photos and synthesis, and then question mark. So each of these will have a number. So S is made into 2, what is made into 2264, this S is made into 16, this photos is made into 2356, and so on and so forth respectively. So now these things are passed into the input layer, and then the model processes it and then it guesses the tokens. So again it will return something like this, a set of numbers, which is going to be our result. Like let's say photosynthesis is a process that the plants use to get food and blah blah blah. Don't remember my 9th standard science. So it basically detects these tokens, and then they are decoded again to form letters. So this is how a model process. It doesn't understand what you're trying to say. It just predicts what you're trying to say. It's like an autocomplete on crack, let's say. So that is how LLMs work. So it's pretty interesting. Now let's move on to the next slide. Yeah. Now before this, so uh, if it has to guess these words, it has to be trained on a lot of data, right? Because it's basically guessing word numbers. It should be trained on a lot of data. So if you remember, I was telling something about the 8B, 7B, and all that in open in the Hugging Face. If I go to Hugging Face, you can see over here, uh, 17B. So these things are called parameters. So what parameters is exactly is, on a high level overview, parameters is basically like having 17B means 17 billion. So it's like having 17 billion knobs. Let's say you have like an 1 millimeter ball which has to go through a tunnel. But that tunnel has 1 billion routing mechanisms to make the ball go in a straight line. So those are these parameters. So they are basically like numbers. So each weight has a significant to generate exactly these numbers as outputs to make it predict stuff. So 17 billion means there are 17 billion knobs that the model can turn, and in which it's trained. So and if you see, I want to say another thing about open source and frontier and open source models. Frontier models, as you can see, Meta Llama is one of the most powerful, and let's say DeepSeek. DeepSeek is now really powerful. It's around 400 billion. Uh, Guess how much ChatGPT, the latest model GPT-4, it's not yet teased yet, but people are speculating it to have 1 trillion parameters. So basically 1 trillion numbers, 1 trillion knobs to give you the perfect output. That is why the model is so beautiful. That is the difference between frontier and open source. Open source provides you free models, but then they are not as powerful. But then you can make them as powerful by fine tuning it, which we'll cover later. And moving on to how LLMs are trained. So training journey of LLMs. So let's say I'm going to train a model, and let's call it something like GPT Express, some name. So what would I first do? So it is just like a model with these 1 billion knobs, but the knobs don't know what to do. They don't know when to put plus, when to turn minus. So these weights are like randomized numbers, okay? The knobs are also called weights. These weights are like randomized numbers. So what happens in pre-training is, so at first it needs to understand our language. So for example, it needs to know the structure of words. So for example, photosynthesis is a process. So photosynthesis is a process that those tokens should be in a particular sequence. They can't be random. To make the model understand, a lot of books, data, news, and everything is fed into the model, and it is pre-trained. So basically, while pre-training, the weights are getting adjusted. When the weights are getting adjusted, the model like understands how these English words work. It doesn't understand, it's like predicts how the English letters work. So it will know when to use photosynthesis, when to use is, when to use the. It like kind of, if is comes, I should use the. It will be like a kind of like that, like guesswork. It will become better. It will understand our language, the sequence of words and all that, and then it will create a dictionary. So I told you, right? I showed you in the code. Photosynthesis was split into photos and synthesis. A dictionary gets formed. A dictionary gets formed in this stage, and each dictionary will have its corresponding number, and all that will happen in the pre-training stage. Next, the model goes into fine-tuning. Depending on the task of the model, a model can't do everything. So there are a lot of types of LLMs. You can give a uh, for example, ChatGPT, if you give a prompt, it will give a reply. So they are basically text-based models. And some models, if you give an image, they will like convert that image and describe it. So those are image to text, and there are text to images, and a lot of models. But a model can do only like one or two things at a time. So we're going to fine tune it. So they basically fine tune the model. So basically they are going to refine the skills for specific domains. So for ChatGPT, it's going to be text generation, something like that. Next is instruction tuning. So this is a pretty interesting stuff. So after pre-training and fine tuning, a model will generate stuff, okay, but then it won't like it's just going to generate. It doesn't understand like what's going on and all that. So let's say humans give text with emotion. So I will give something like, give me a 2-line summary of this. LLMs are beautiful. Okay, something like this. So the model will read this. Okay. The funny part is, at this stage the model is just like an autocomplete on crack. It doesn't know what's going on. So it is just, what it does is, it won't understand the statement. It will just continue this statement. LLMs are beautiful. They are really great. It will provide this type of result, and then it will generate blah 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 blah, as you say. I don't have to tell that. And so instruction tuning, what it does is, now the model needs to know what you're trying to actually ask it. So the weights are more, the knobs now needs to understand what this actually means. So what happens is, when you're training a model to understand human emotions, you will basically tell, give me 2-line summary of this. So this has a particular importance. So the model will basically learn. If you, when in instruction training, the model will basically learn these things. So after you instruction train it, what it does is, give me a 2-line summary of this. LLMs are beautiful. It will tell something like, LLMs are beautiful is conveyed by the user, and something like that. So basically it understands this statement. It doesn't just complete auto completes the statement. So this is what happens in instruction tuning. And then finally it is RLHF. RLHF is reinforced learning from human feedback. So basically if you see like when you're giving an instruction to ChatGPT, it will randomly give whenever you're desperate for a result, it will randomly give this two boxes of two random results, and then that'll be, I prefer this response and I prefer this response. Be pretty annoying sometimes. So that is basically RLHF. So before, RLHF happens after the model is trained, but usually RLHF is happened after instruction tuning, before the model is deployed. So basically the responses given by the model are marked as good, bad, and something like that, and then it's reinforced learn. If you know reinforcement learning, you should know concepts like penalty and reward. So basically a penalty or reward is given, and it reinforces itself, and the weights are finally, and then at last the model is ready for consumer usage, and then the model is deployed. So all this takes a lot of time and a lot of GPU and a lot of resources. So it's a pretty tedious process, and beautiful what the engineers have done. And moving on. Now let's move on. Now that we know how LLMs work, how they are trained, let's move on to using LLMs. So how to use them. So we have used them before, like we just ran a code and then result came. So I'll explain the code, what's doing. APIs and prompting. So we basically used Hugging Face transformer to connect the model, and there are two techniques. And to use these APIs, there are two techniques. One is using pipelines, and other is using inference. Each one has its own advantage and disadvantage. So over here, let's move on to the code. So as you can see over here, I have used transformers, transformers to, and then I have used pipeline over here. So basically what it does is, you can see I've used pipeline over here. So basically what it does is, it loads the weights of the model in your local system. So basically it loads this model into my Google Colab. So basically this model right here is about 7 GB. As you can see, my local RAM is like belted over here, 7 GB. And it basically loads the model inside your CPU, and then the model uses your CPU resources in order to give you the output. So when you're prompting it, it uses your resources to produce output. That's why it took around 42 seconds for me. This is lesser time because at first you have to import the model. Importing the model takes a lot of time because it's about 7 GB you have to download. I've already downloaded for the session, so it was faster. It usually takes around 6-7 minutes if you're running Collab CPU. GPU is much more faster, and I'll explain the code what's going on over here. So this is the Hugging Face library, transformers. I'm importing auto tokenizer, which is used to tokenize, auto model for casual LLMs, which is like a package for importing already pre-existing models on Hugging Face. So, and then casual LLM meaning it's like for chat, text to text purposes, that type of model, and then pipeline. And then here I'm giving the model name, which is Facebook's opt, and then here I'm loading the tokenizer. Here I'm loading the model, and then here I'm generating. So generator, I'm creating like a pipeline. It's called a pipeline. So what would a pipeline contain? It will first tokenize the model. It will first import the model and then get the model's tokenizer and then proceed with this thing. So generator equals pipeline. This is the task. This is basically text generation, and model equals model. So we'll be basically loading the model, which is nothing but model name over here. You can see from pre-trained, I'm loading Facebook, and then tokenizer, what tokenizer I'm using, which is basically Facebook's tokenizer because it understands only its tokenizer. Each model has its own tokens. Okay, so and then you're giving a prompt, and then a response is generated. So I'll explain what is this. This is basically the prompt. Max length is what is the length of the output you need. Max length equals 100, meaning is 100 tokens, and then do sample equals true, and then temperature equals 0.7. So what does do sample do is, let me open my docs. So do sample, what it does is, why is it slow? Yeah. So what does do sample do is, let's say for example, there's a sentence, photosynthesis is a dash. So there are now the model is like an autocomplete, right? It will generate like, let's say like an MCQ, 4 options. Is a process, survival technique, and then so on and so forth. And each of these things will have a weightage. So for example, this might have 80%. This will have like 10%. And then let's say something below has like 5%. And then let's say something below has another 5%. So what is 80%, 10%, 5% mean? It seems it is the most probable token. So the model wants to use process because it is the most highest probable token. But if it uses this, every model's output will be the same. To add a little bit of spice to it, if you give do sample equals true, each of these things, it becomes on a random basis. So all the weightages don't matter here now. So suddenly survival technique will come. Suddenly some random word will come. This will change the model's output. And like it will make it different. It won't be like stagnant, constant, same words. This is a process and all that. So it basically spices things up, and temperature equals 0.7, and that's a pretty interesting thing. So temperature equals 0.7. What it does is, so it's basically how a model hallucinates. So it ranges from 0 to like it goes on, and what I'll tell you what hallucination is. So let's say for an example, once upon a time was a dash. So this is your so basically this is your prompt you're giving the model, and now we want you to give a result. So when the temperature is low, the model hallucination is at its least. So it will give something like 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 not like a drunk person. It will give something like once upon a time there was a young man. Let's say this thing will when temperature. Let's say for example this let's say this result will give like when the temperature is low, which is at the range of 0.5 like that. When you slightly increase it, it will give like there was a princess wearing pink dress, something like that. Here temperature is slightly higher because it has used more imagination. And then the crazy one, this thing even you won't understand what it's trying to say. Like let's say once upon a time there was a rainbow spitting out skibidi toilets, something like that, some gibberish, some brain rot, something. It just gives something out of the random. So here the temperature value will be really high, which is above like 1.5, something like that. So that's what temperature does. It basically shows the degree of how much the model can hallucinate. So with that, I think the pipeline code is over, and then you print a response over here, and that is one of the ways, that is using a pipeline. This is pretty slow because it uses your resources, consume resources. That will be your downside. Upside will be basically you have all the whole power of the model with you, so you can do a lot of stuff with it. You can even fine tune it. So the other method is using inference. So over here I have used inference. So inference, what it does is it's like an API call. It's like basically using ChatGPT. You give a request, the model is hosted in its own GPUs and all that. It'll give a result instantly. And then you can see, I'll show you over here. Here I'm loading a 7 billion parameter model. It's not a 1.5 billion model. So it's like a more powerful model. And over here I'm giving it prompts. Um, combine tokens, max token, temperature, do sample, and then printing response. Now I'll run this. It takes literally 0 seconds and the result has come. So it's pretty quick. But then the downside of this is basically you're using API, and then API is not free, and then because hosting is not free. So basically that is the limit of inference. It is fast, but usually they give about Hugging Face gives about $5 of inference. You can there are other websites like Grok AI. So you can use this thing. This thing is also pretty good. This thing also gives you about $5. You can go to Dev Console. And one problem with Hugging Face inference, which I've used here, is you can't use models like Llama. You can only use them in the paid version. You have to like pay a subscription fee and for you to use it. Grok gives it for free, so I feel like Grok is a little bit better. But then, so there are a lot of models like text-to-text reasoning, coding, function calling, tool use, and all that, multilingual. So there are a lot of models, and you can just import them and use directly. And you can create an API key over here, and it's pretty well documented. You can use Grok too. It's also a pretty good website. Moving on. So these are the two methods to use API calls to call a model. So one is using inference and one is using pipeline. Each has its own advantages and disadvantages, as I've explained before. Moving on to prompting techniques. So you would have seen this variable called prompt over here. User prompt, system prompt. That is basically the question you're asking it. So for example, if you type to chat GPT, what is an LLM? That is basically a prompt you're giving it. So here you can more customize your prompts more. So what you can do is there are uh, zero shot, one shot, multi shot, and chain of thought. So I'll go one by one. First, I start with zero shot. Zero shot is something that you give the model directly and hope that the model understand what you're trying to say. So for example, and hopefully it gives the result in the way you want it. So for example, if you give uh, mm, let's say translate this into Spanish. Hello, how are you? So this is basically zero shot prompting. So you're basically giving everything to the model's hands, and then hopefully you hope that it understands this what you're trying to say here, and it gives hola como estas, and that is zero shot prompting. And then one shot prompting is you're going to give one example of what exactly you want. So it will be something like example um, question. No. English. Hello. How are you? Spanish. Hola. ¿Cómo estás? And now you give. Now convert this using Spanish using the example above. And then you give an English text. Now the model has an example to work with. So you have better chance of getting better results. So each one has its own use case, and you can give something like blah blah blah. It doesn't matter over here. And that is basically one shot prompting, giving one example. And then multi-shot prompting. Multi-shot prompting is basically giving one or more examples. Oh no, backspace. Yeah, multi-shot prompting is basically giving more examples. Like you just change these sentences. I just know three words of Spanish, so I just use it over here. Yeah, it's basically giving more examples. So you have a higher chance of using them, getting a really good result because the model has exactly what you want the result to be. It'll be useful in coding processes. Like if you give me a code like this but with this, so you're basically using a one-shot prompting in those cases, or a multi-shot prompting depending on the number of examples. Uh, yeah, and then at last, chain of thought. Chain of thought is basically asking the model to give how it thinks that way. So basically, it's very simple. So let's say you're solving. Um, Give me the answer for integration in integration of x square of plus x dx, something like this, um, and then give me the steps of it. So basically you're asking how is it thinking by asking it give me the steps. So how will it reply to this is it'll basically for x and this thing, and then give like a stepwise answer. So it will be useful for max and all those types of outputs. So depending on the output you want on your website or whichever you're using these LLMs for, you can use these types of promptings. So it's a really important thing. Prompt engineering is a really important thing. Earlier there used to be posts like prompt engineers. So these guys used to get a lot of money. You would have seen those 7 rupees wala chat GPT courses. Use this chat GPT course and then you will become master of AI, something like that you will see. So those courses are for prompt engineering basically. Nowadays you can just prompt engineer using chat GPT. Give me a proper prompt for this so that even you understand what you're trying to say, something you can do like that, and it only gives you the prompt. So those jobs are now reducing. Um, so these are some of the prompting techniques, and let's move on. Yeah, now let's move on to the most fun part of the session, which is basically fine tuning your own model. So this is the most like important part of LLM. So you can like fine tune these huge models and then make them perform even better than ChatGPT for a particular task. It's like you have heard Bruce Lee saying, "I don't fear someone who has practiced 1,000 techniques 10 times. I fear someone who has practiced one technique for 10,000 times." So basically, these small models can outperform ChatGPT. So it depends on how you are going to train it. So there comes QLoRA, which is moving on to the code. So this is QLoRA code. Um, so it's the same code. You basically get the token. Wait, let me connect to my GPU. For QLoRA, you have to use GPU. You can't run it on CPU. It doesn't allow you because it's not possible to run it on CPU. Let me change runtime. Run this. So one of the problems with pipeline is, as I had told before, uh, it basically imports imports the model into your local system. So these models are huge. They are like 4 GB. 4 GB is for this model. It's like pretty small. Let's say you're loading Metalama or something like that. They go up to like 16 GB, 20 GB, depending on the model. Uh, DeepSeek's 403 billion parameter model goes up to, I think, 300, 200 GB, I believe. I don't remember properly. So it's like really huge, right? So you can't run it on your local machine. It's not like possible. So what you do is there's something called quantizing an LLM model. So quantizing is a really good concept. It is basically, so what are these models? These models have these parameters, like the 1 billion parameters, 10 billion parameters, and all that. Oops, I closed my Google Docs again. Yeah. So the models have like these parameters like 10 billion, 12 billion parameters and all that, right? So all these parameters have like a number, because you're passing numbers, you tokenize and then you're passing in numbers, and then these numbers it guesses and all that through these weights, and then it comes out. So these weights are like 1 billion numbers like this. That is why it's like so huge, like 16 GB and all that. 1 billion numbers like this carry about that much space. What happens if you quantize it is, so this number while loading becomes something like this. It lowers the precision by a lot, but it also lowers the weight of space taken by the model by a lot. From 16 GB, you can convert the model into just 4 or 5 GB. So here, yeah, yeah, let's run this code. So I'll show you. So you're basically what you're doing is, while quantizing, you're converting something this big to just something like this. So 1 billion of these will be like 4 decimal point numbers. So it lowers the precision, but then it reduces space. So basically, I've already run it. It takes some time to run. I'll just explain what's going on over here. So it converts these huge decimal numbers into these small decimal numbers in order to save space. But then obviously it might be weaker because of 16 GB is converted into 4 GB. But then it's not that bad. It's actually good. It's actually usable. So so I'll explain this code. So I'm loading Metalama here. I think you should know what this model is, and I'm using bits and bytes. So this is what is used for quantizing a model, and load in 4-bit through. So this is basically converting the whatever, let's say 16-bit float value. So basically the number over here, let's say 16-bit to a 4-bit. So it's converting into bits. And then this is the most important part. It's like a very interesting part. So while loading the model, you load it like this to save space. But while computing and giving the output, you convert this into something like a similar number. You convert this into a similar number. Just leave the numbers, I'm just typing randomly. Something equal to this. It will be as close to these values. And so if you think about it, you are actually using these numbers only. Like while loading, you're loading only these four numbers. But while calculating, what you're doing is you're basically making it something as close, because there will be like a lookup table. So if let's say it like a lookup table, so 0.8934 correspond to something like this. So it will be like that. So while calculating, while using it for calculations, you're using it as a 16-bit. So that is why the model's quality doesn't diminish that much. So that's why even if you convert it to 4-bit and download, you're calculating, while you're calculating, you're using it as a 16-bit. So it doesn't like hamper the process that much. So it's like a really good thing. And this is why quantization is a thing, or else quantization won't be a thing, because zero using this as weights is just absurd. It's like saying this number is zero. That much difference it makes. So it's not possible, right? So it's a pretty good thing. And BNB 4-bit use double quant equals true, type equals NF4. So what it does is NF4 is like let's say way to convert a 16-bit floating point number into 4-bit floating point number into quantizing, while retaining most of its value. So while calculating, you're converting it into a 16-bit, right? To make sure it comes as close as the number above, which is the original number, NF4 is used. It's like a really good technique. It's really good. So every LLM uses this. And moving on, so here's the same thing, tokenizer. I'm tokenizing what it's doing. Model, I'm loading the model, and here I'm giving the quantization config. So basically the model knows to config. So and then the same code, literally the same code. Um, so I run it. I'll show you. It downloads stuff. So here you can see that the model is loaded, and look at the result. Keep in mind that this model is 1/4 smaller than the original Llama model, which is basically a 16 GB model, and now it's just 4 GB. But still you can see the results. They are beautiful. It has even given a breakdown to me. So that's like really good. If you think about it, it's like beautiful. So you're basically using a 4 GB model, but then that 4 GB model gives this beautiful results. So that is the beauty of quantizing. So whenever you're training, you try to quantize the model. You can train without quantizing the model, but then it takes more time and resources. So it's better to quantize because it doesn't hamper the process much. It is much faster. So why won't you do that? So it is pretty good. And to so moving on to fine tuning. So basically, so how do you can't train an LLM from scratch, because I told you how to train an LLM from scratch, right? So it's like a pretty tedious project. It will cost you like 2-3 like millions of dollars. So it's not possible for us. So we do something like low rank. It's called low rank adaptation. We use the technique called parameter efficient tuning, fine tuning. These words are not important. If you want, you can remember them. I don't usually remember them. So it's basically you parameter efficient fine tune the model. Basically fine tuning the model for your own particular use case. So let's say I want this GPT model to generate only code for me. So I'll give you basically by like training a deep learning model like a neural network. I'll give it input output and then it trains accordingly. So I'll explain how it works. So basically, this is the code. I won't run this code because it takes 48 hours to train a model on like T4 GPU, which is pretty long time. So it's the same thing. I'm basically quantizing it here, as I've explained quantization above, and I'm using Mistral model here. Mistral is another open source really good model, and then I'm using its tokenizer. It's the same thing. So here you can see something called LoRa config. So this is how you are going to fine tune the model. So you're configuring the LoRa. LoRa is nothing but low rank adaptation. So basically what is happening is there are these layers, like each model like has like layers. So LLMs have something called self attention layers. So these are the most important layers. Like these are what make the LLM an LLM. So they are like far better than faster and than RN and CNN. You may so basically what you're doing is you're fixing two layers onto these self-attention layers. So basically you're not touching the original model's layers, but you're adding two layers of your own. So basically that layer, you're training it, you're basically training that layer. You're not touching the model, but you're training that layer. And then you're fine tuning. That's why it's fine tuning, because you're not touching the learning. It's like transfer, it's like something like transferred learning. So I'll show you. It'll be better if I put it on paper. So let's say the original model's weights, like it's like it's stored in W. What you're doing is you're so basically when it's doing tasks, it'll be this. So input will go over here, it'll go to this, and then output will be generated by this. Oh, output. Oh, output. Okay. So when you're low rank adapting, what you're doing is, hey, I'm going to add two extra layers. So these layers will be of this form. W, it will make the model as W plus A into B. So you can see that these two layers are added to the original model. The original model is not touched. Just two extra bits are added to this. So you're basically going to change these values. You're not never going to touch these values, because it takes as I told, it's basically training your own LLM if you're going to touch this. So you're basically going to use just to these layers, and then you're going to generate output. Now input will be generated like this, which gives you the output. So this is how low rank adaptation works. So now I'll tell you the parameters of low rank adaptation. So yeah, as you can see, there's something called R equals 16 here. So what R equals 16 does is, let's say W, oops, my keyboard stopped working, throw it away. Yeah, let's say W equals 4096 into, let's say it's like a matrix of 4000 or 4096, like 4000 inputs and then 4096 outputs. So here, if you give something like R equals 16, so the equation is this, right? The equation is something like W plus A into B, right? So if you give R equals 16, A's value will become 4096 into 16, and then B's value will become 16 into 4096. So basically R value determines how complex you want the layers to be. So more the R's value, you're giving more space to the model and be better. But then if your training data is too less, it will start to overfit. So it's better to keep something like 16, so standard value, if you're going to fine tune the model. And so now what happens is, now multiplication makes sense. So it becomes 4096 1 second. Yeah, now this value is 4096 into 4096 plus 4096 into 16 into, so basically it's like a matrix multiplication, right? So the rows and columns should match, into 16 into 4096. So now it makes sense. Now when the 16 and 16 combines, it will become a 4096 into 4096 layer. This is how the adaptation works, low rank adaptation. And LoRa alpha. So LoRa alpha, what it does is, how much impact do you want this thing to have? So I've set that value to 32. So what it does is 32 divided by the R value. So it will have 2 times more impact on the output. So how much do you want these things, so these two A and B, to impact the output? So that is what LoRa alpha is. So it basically defines the impact. And then the target modules. So target modules is basically which layer do you want the adapter to fix. It's basically two self-attention layers, and they're the most important layers. So we are, for most of the tasks, it's QProj and VProj, and we are basically adapterizing those layers. And then LoRa dropout. If you know neural networks, you must know dropout. So basically during the in high level terms, if you don't know what a dropout means, so basically this 4096 into 16 matrix of this is there, no, and the 16 into 4096 matrix of this is there, right? So basically uh, during the input layers, you're going to nullify some of the weights. So you're going to basically make some of the weight values as 0 to prevent like overfitting and all that. It is a regularization technique. So basically you're going to like reduce the chances of overfitting by dropping out some of the weights. And then task type. So task type is basically what type of task do you want it for. Here I'm using casual LM, so it's basically used for text generation models and all that. So it will change model wise, and then you're going to load this config into get pef model, and then you're going to load your data set. Data sets you can get a lot, as I showed in Hugging Face, like a lot of beautiful data sets. I think that is slow. Yeah, there are like a lot of data sets. You can search data sets. There are about 355,000 data sets. It's like a huge number. And uh, now after that, you're going to, so these data sets have to be in a specific structure. If you have trained neural network models, you will know it. But for high level, there should be an input and output. So basically, you're going to fine tune the model. So how will you fine tune the model is, because you want it to provide a specific result. So you will give an input and an output. So basically the model will train basically with the input and output, and then it will adjust the weights accordingly. And then you're going to tokenize these inputs and outputs, and then you're going to tokenize these data and then create a training class, and batch size, basically number of batches of training data you want per epoch. So for per iteration, number of batches of data you want to be pushed, number of epochs. So how many times do you want to run the model through the data set. Learning rate is self-explanatory. So basically how fast do you want to make the model learn. Um, and then you train the model, and then you get the fine-tuned model. So this is how you train a model. So you use QLoRA. You first quantize the model, and then you use these adapters to train a fine-tuned model. And now you have your own fine-tuned model which you can use. So you can also host these models on Hugging Face, and then you can directly use it in your code by using Fast API and transformers. And this is how you fine-tune a model. So with this, we'll be moving on. So now I'll be showing a live project demo. So this is a project I created at a hackathon. So I'll explain the problem statement. Before that, I'll run it. CD backend. npm run dev. So the project is basically tech stack is Python, fast API for backend, and then VIT for frontend. So I'll run this and then explain what it does. So this is the front end. Let's see if the backend is loaded. Okay, so the backend is loaded. I'll just start uploading the data because it takes quite some time. It takes about 7 minutes. Um, so I'll move on to the problem statement. So the problem statement is something like so each company has like these annual reports that they publish at the end of every annual year to show what their company has done, what's the finance situation of the company and all that. So you can see that this is a huge like 159-page document of random stuff that no one will read. It's just for formality purposes. It's just a huge document. It goes on forever. It's a 159-page document. So the problem statement was to analyze these documents using Gen AI and LLMs and then give possible red flags and green flags of the company based on the annual report, a story based on the company, and then uh, other stuff like visualization, like it's like extras. So I'll now tell what me and my team have done. So okay, so this is the flow chart of what we have done. So basically, from the web interface, the user will upload the annual report, which I just did. You have seen that loading. Okay, yeah, you have seen that loading, and then as a module in Python called PDF Plumber. So basically, what it does is these annual reports. It basically scans these reports and then gets the text, and then we can store it in a variable. We can store it in batches and do all kinds of stuff. So basically, it takes all the text in the PDF document, and then we are using NLP techniques in order to extract like only few data is needed because I just have to generate red flag things. I don't need stuff like random stuff. So we are using NLP techniques in order to classify the data as financial data and non-financial data, which is using SPACY and name entity recognition. So I'll give you an example of what it does. So basically what it does is um, let's say there's a text. Um, uh, this company is having this much in its cash flow, this much in its revenue, and so on and so forth. So basically, revenue is a financial word. So basically, it knows which is a financial word and which is not a financial word. And then there's a lot of classes. So basically, it's like a pre-trained model. So we basically classify financial and non-financial data because we don't want to pass everything to a model. So it's like a pre-processing technique. And this data is sent to our financial summarization model. So this model basically takes in the basically takes in the input from this and then it basically summarizes it, and then it gives the overall performance of the company for the financial year, which is then passed through our fine-tuned frontier model. So we have basically fine-tuned a frontier model because the hackathon was about 8 hours. We couldn't fine-tune a model using QLoRA because it'll take like 24 hours to train. So we use a fine-tuned a frontier model, which is much easier, and we generated a story using that story and red flag, green flag, and all that. And the other stuff that we did this, so using this data, you can also extract the company's name. So using the company's name, we used Yahoo Finance, which is open source, and then we retrieve the balance sheets and income statements, cash flow of that, basically financial gibberish and all that. And then using that, we created graph and visuals, and then we used Google News, and then an interesting aspect of what it does is So basically, we use the Google News in order to like uh, see people's review about the company and then compare it with the financial annual report and then check if it's matching to make sure that the company is not just giving some random like hyped up stuff. So it makes sure like it aligns with the people's emotions. We use a sentiment analysis model. So sentiment analysis model will give like it will compare two things and it will give positive sentiment, negative sentiment, something like that. And then we give all these things to user. So let's see if it is generated. Oh, oops, it's still generating. In the time, um, oh, is it generated? Is it still generating? Yeah, yeah, you can do a lot of beautiful things with LLMs. So I'm just trying to while away time at this point. Loading takes some 7-8 minutes. So while loading, I loaded this Reliance document. Okay, it's taking longer than usual. Did it throw an error? At last. Yeah. So so this is the result, and as you can see, at first I mentioned that it first gives some financial summarization model. So this model gets gibberish, okay, just like numbers and sentences, random sentences. So it clubs these sentences, and then it's somewhat gives like a summarization. You can see that over here. It's like a huge thing. Um, It gives pretty like relatable stuff from the document. So this thing is given to other models like a fine-tuned frontier model to generate red flags and green flags. You can see Reliance net depth of 38,340 crore, a lot of financial stuff. If you have any question like we have integrated a chatbot. So this thing uses Grok inference and uses Google's Gemma, and this is like a basic chatbot, and uh, and then there's a positive indicator. You can see that something this huge, that even like if you take like 1 year to understand what it does, it'll take like 1 year to like understand what they're trying to say. In a matter of 7 minutes, you get something like this. You get like a summary, you get like a flag, you get like a story. Even like a layman can understand this thing. So this is the Google News stuff which I told. It compares the annual report with the feedback from Google News, and moving on to visualization. This usually gets the stuff like cash income, like income flow and all that. Forgot those terms. Really bad at finance stuff. Yeah, it retrieves balance sheets, income statements, and cash flow. So basically, these huge Excel documents, it basically gets them and creates these graphs. So this is the project I did for my hackathon, and it's a pretty good like. I mean, it's like converting like something which is like impossible to read and something is like really beautiful, and this couldn't be done in 2 years before or 3 years before LLMs were launched and everything. So this opens a lot of opportunities. So with this, I think I'll end the session. So if you have any questions, you can ask me. Mm, okay. I think there's like a 2 minute, 3 minute delay. I don't know, for some reason chat is not loading on my VIT. Let's see if it's loading on my system. So any questions? So I think no more questions. So I'll end the session. Hope you learned something from it, and welcome to the world of LLMs.